Um, okay, so we talked about limits a little bit once again. It's of course similar to limits when we're just talking about one variable limits. Limits of something that is a one variable expression. And of course, it's really nice when we run into one like this because it looks pretty complicated. Limit of cosine of 25 minus x squared minus y squared over x minus y. And then if we really think about what this means, okay, so I'm trying to take this expression, which, you know, that's a pretty complicated, if we think about the graph there. And this even complicates it more, okay? So let's just say that's a circle, I mean a sphere or something like that. And we're coming in to this point on the graph of that thing. Well, if you think about it, coming into that point, that means you're coming in from all directions potentially. So we've got this surface, whatever it is, okay, and I picked out this one point, right? And so I'm coming in to that point, but I can come in from all directions. So this could be a pretty complicated deal. But we like it when it's like this because the good news is, yeah, just like previously, if we can substitute the values in, that's going to be the way we back with this limit. I mean, there's more, of course, to it there, and but we'll talk about some other things as we go along here. But this was pretty easy because it's just going to be cosine square root of 25 minus the x is going to 3, so it'll be minus 3 squared minus y, which is going to 4, over x, which again is going to 3 minus 4, because that's going to be the value of this limit, because this function is defined at those particular values. And we can plug it in. Right, because that's cosine of, that'd just be cosine of 0 over negative 1, which is 1 over negative 1, which is 1. So, again, without going through the whole table sort of thing, because that's what we did when we started with limits, is we said, hey, look at this table. I guess that was the very first thing we started with in calculus, right? We took a table and said, hey, this looks like it's going to this. Well, it turns out that, yeah, if you just plug in the numbers, you can get that limit. Same thing here, so that's good. Even though it may be a little more complicated. All right, so now, yeah. Of course, what will happen is we run into this. We will get limits where the limit is not exactly, we can't substitute in to get the limit here. Right, because it's our old buddy 0 over 0, isn't it? And unfortunately right now, we haven't talked about derivatives. That's where we're going actually next after we talk about limits, but we haven't talked about how to do derivatives of two variable functions, and so L'Hopital is not an option either right now here for these. But here's what we might start looking at. All right, so we've got 0 over 0. We will look at ones, and maybe I should have started with those, but we will look at ones where we can do factoring. Remember on some limits previously, we did some factoring. that's still an option. You can still use a factory if it helps. What else we do? Conjugates. Took the conjugate, multiplied by the conjugate. That's still an option if it applies. Not so much here. Okay. So again, this one, doing this one because it again kind of stresses what we're doing here. Okay, so if we're thinking about xy approaching 0, let's just think about the xy plane. So I'm approaching this 0, 0, and it doesn't necessarily have to be there, but yeah, and I kind of hinted at it up here. What that means is I could come at this 0, 0 point not only from along an axis, but I could theoretically approach it from any direction, from any line, not just an axis. You know, I will think about, well, what happens if I just come along at it at an axis, x-axis, y-axis, you know, something like that. But I can approach this from any line, as long as, you know, you get to 0, 0 there. And even further to complicate it, it could be from any type of curve I could approach it. That can be helpful too sometimes. So you get the complicatedness of this, right? This is coming at it from all directions. 0, 0. All right. Well, sometimes if you approach it along, you know, different lines or different curves, you get two different values. And of course, you know, if we get two different values as we approach it from two different ways, that of course means the limit doesn't exist. Because they've all, for this limit to exist, any way we approach that 0, 0 point, it has to have the same value. Okay? And so that's one way to do this, to answer this question, is to find out that it doesn't exist because there's two different values for the limit, or two different values as you approach that 0, 0. So anyway, so let's think about this one. All right, so this one is an example. Let's approach it along the x-axis. Which means our, so this is our f of x, y right here that I'll refer to. It's y over x. So as I approach along the x-axis, the points I'm talking about would be what? What form are they? What, comma, what? Well, if I'm approaching 0, 0 along the x-axis, the points are all, they all have an x value, but the y value is 0, right? So as I approach along the x-axis, those points I'm coming along at are all x comma zeros, right? All right, so what is f of x comma 0? Well, that would mean the y is 0, and the x is x, but that's just 0. So our f of xy, in that particular case, which is f of x 0, the f of xy would approach 0, it is 0. Okay, it's always going to be 0 in that case. So, all right. Now, let's approach it another way. Now, it doesn't, it wouldn't do us any good here to approach along the y-axis because that gives us just undefined there, but that may not necessarily mean anything. But let's approach it along a different line Let's approach it along the line y equals x. So when you're doing this, what you're looking for is, well, is there another way to get a different function value out of this other than 0, since I got the first one I got was 0. So, I mean, if you can't come up with another value besides 0 or 1 or whatever it is you first came up, that's maybe pointing to this limit does exist, but you'll see what I mean. All right, so as we approach the line y, along the line y equals x, the points are, well, since y equals x, they would just be x comma x's. You see what I'm saying? The x and the y are the same. I mean, you could do y if you want to. So that would mean our function value is now x comma x, which would mean the x and the y are x. So that would be x over x. Hey, look at that, that's 1. So fxy goes to 1 as we approach, or as, let's say, as xy approaches 0, 0 along y equals x line. Okay, this is as xy approaches 0, 0, but it's along the x-axis. So you see the problem there? F of xy approaches two different values as you come into 0, 0 along different lines. So that limit doesn't exist. Okay. Back there. Any questions about that? So sometimes, yeah, you can substitute it in. Sometimes you can come up with two different values. And that means the limit doesn't exist because it's always got to be one value. All right, let's look at this one. What about the limit as xy, which is 0, 0, 2x over y squared over x squared plus y to the fourth? So again, we got the 0 over 0 thing. But as we know, 0 over 0 is indeterminate. So we got to figure out if there is a limit or maybe there is not a limit. Well, again, if we look, look for obvious things like factoring or conjugate, something like that, but here, there's nothing really that's jumping out as far as factoring goes. So, and we'll talk about some other things too, but for right now, nothing really jumping out to me. So let's just try some things. Let's again look at along maybe the x-axis, or y-axis. Again, that's points over x comma 0 along the x-axis. So that would be f of x0. So just see what f of x0 would be. So that would be the y is 0, so that'd be what? 0 over x squared, so that's 0. Okay, 0. And you could try the y-axis, but that's not going to help me out because that would be 0 comma y's, right? we come along the y-axis, so that would be f of 0 y's, which is 0 over y to the 4th, so that's still 0. So that's not a counterexample, if you will. All right, so what other kind of counter thing? We looked at, last time we looked at the line y equals x, but that may not be helpful as well. What you want to look for is something that gives you something that would reduce, like if I did y equals x, that would give me f of xx, which would be 2x over x times x squared over x squared plus x to the 4th. 2x cubed over x squared plus x to the 4th. That's not going to help, okay? That's still 0 over 0. So what I'm saying is, look for something that that kind of helps you simplify things. And so in this case, let's do, I think I said, yeah, let's do x is y squared, which is a curve. Kind of a sideways parabola, right? Because, like I said, we're approaching 0, 0, in this case it's 0, 0, from all different points, or all different kinds of curves. So it can be a line, an axis, but it can be just a curve. You know, that's going to come into 0, 0, right? That's the only thing that you have to be, x, y has to come into that point at some point. Or that curve has to come to that point. Well, you see why that's helpful, because that would be points in that context would be the x is y squared, so it'd be y squared y's. You see where we're getting that? The x is y squared, so it'd be y squared y's. So what is f of y squared y? Well, that is 2 times y squared over x squared, so it'll be y squared squared plus y to the 4th. So you see why I picked that? Because that's 2y to the 4th over y to the 4th plus y to the 4th. That's going to simplify. It's going to simplify to 1. So that's the kind of things you're looking for, is you're looking for something that's going to simplify to where it helps you. I've got one way is coming to 0. Well, actually, 2 ways coming to 0. This didn't really help me any, because I guess that would simplify, but it's not going to simplify to anything other than 0 over 0. But I don't know. Maybe we could use that. But do you see kind of why this? So now this tells me, all right, so this shows me that the f of x, y is going to go to 0 along that line, along that axis. This one shows me f of x, y is going to go to 1 along the curve x equals y squared. 2 different values. Therefore, limit does not exist. These two, or that one is what I'll do. You see kind of the idea here, and it's usually different for all of them, but just have to play around a little bit with it. Does not exist. 2 different, probably all from different values. Those 2 are. Okay. Yeah, so let's look at some where maybe it's a little more obvious. So what's the limit? X, Y, there's 0, 0. There's a lot of those. Look at x squared minus xy over square root of x minus square root of y. Yeah, that's the kind of thing I'm talking about here. We're looking at that, and 0 over 0, of course. And so if there's something obvious that jumps out at us, then let's try to, it may not work, but this one, hopefully here, you're thinking conjugate. Is that what you're thinking? Hopefully you're thinking conjugate. Yeah, I got a conjugate in the denominator, a square root, 2 square roots in the denominator. So yeah, let's try our conjugate thing here. Seemed to work sometimes previously. Yeah, let's just leave the top alone because the conjugate's in the denominator. Conjugate's bottom's x minus y. Yeah, that, and matter of fact, let's factor that, save us a little bit of writing there. Yeah, we can factor, instead of multiplying, we can factor that one because if we do the conjugates in the denominator, we get x minus y, right? And so that is going to wipe out. And so no longer do I have 0 over 0. Now I've got 0 times 0, which that is not determined, that is 0. So, yeah. So sometimes those things work. That one's got the factoring and, well, the conjugate and the factoring. So there's those. Can try those. But there is one other thing that sometimes can be helpful, especially when you do get a limit. Any questions about that one? The other thing that I don't think we've used previously, but it's called the squeeze theorem. That's another tool here that we can use in this case here and other places too. But the squeeze theorem is this: if f of x is between two other functions, we can set up a inequality like on the one hand we've got g of x is less than or equal to f of x, and then also f of x is less than or equal to h of x, so we can just write it as a three-parter there. So if we've got f of x is between two other functions, basically, and we can figure out that the limit, in this case we're just using a one variable example here, but the limit as x approaches a of g of x and the limit as x approaches a of h of x equals the same thing, L. Then, by this squeeze theorem, the limit as x approaches a of f of x equals L. So that's the one variable that can be extended to the two variable counterpart. Called the squeeze theorem. So these two, so we've got f is between these two, and these two go to L. Well, got to squeeze in there. F has to go to L, so to speak. A good example, the one they do in the book back in previous sections, is this one. For example, if I'm trying to find the limit as x approaches 0 of x squared times sine 1 over x. This is my example of the squeeze term. Well, on these, what you do is kind of start with something you know. I know, is there an inequality I know that I can set up here? And what we're going to do is play off of the sine 1 over x. Sine has, no matter what we're doing the sine up, sine is always between -1 and +1, isn't it? That's just a fact about sine, okay? Sine has to be between -1 and +1, no matter what you take the sine up. So sine of 1 over x has to be between -1 and +1. All right, well, if I multiply here by x squared, everything by x squared, well, that's a positive number that I'm multiplying by because x is x squared, no matter if x is positive or negative. That's a positive number, and so multiplying everything by x squared doesn't change this inequality because I'm multiplying by a positive number. If I was multiplying by a negative number, I'd have to flip signs, or it could be positive or negative. I might have to think about that, but this is x squared, that's a positive number. And so that by x squared gives me that. That by x squared, of course, gives me sine x squared times sine of 1 over x. That times x squared is x squared. So the inequality doesn't change, except I multiply everything by x squared. Well, now if I take the limit as x approaches a, here it is, which in this case is 0. So take the limit of each one of these as x approaches 0. What do you got? 0 less than or equal to, and we'll write that, that's what we're trying to find, the limit as x approaches 0. X squared sine of 1 over x. And the limit as x approaches 0, that is 0. Look at that. We've got the limit of these two things right here is 0, and this is our limit we're trying to, they're both equal to 0, so doesn't that make this one, yeah, it kind of squeezes it, if you will. And if you look at the graphs, you kind of get the visualization of the squeeze there between x squared minus x squared. Yeah, so if the limit is, another way you look at it, if the limit of this one, if 0 is less than or equal to that limit, meaning this limit is greater than or equal to 0, but at the same time it's less than or equal to 0, it's got to be equal to 0, right? Any way you slice it. So that's kind of the idea, and so we can use that also here. So that's by the squeeze theorem. All right. Take a look at an example of that one. All right, let's do this. All right, so we got the limit as xy, which is 0, 0. And it's xy times x squared minus y squared over x squared plus y squared. All right. So we're looking at this. Potentially, almost feels like maybe factoring, but really is factoring going to do much here? I could factor the top, At the bottom, not so much. There's not going to be any cancellation if I do the factoring there. So factoring's not, it's probably a wild goose chase right there. So sometimes you can factor with that. If it's no canceling, that's not going to help you. Conjugate, nah, don't have any conjugate here. So those techniques are out. And like I said, if you looked at maybe some, like along the x-axis and then looked along, if we looked along maybe y equals x, we could try some things, but actually this was going to be a squeeze theorem. Yeah, take a look at this. All right, so our known fact here is a little something different. I'm not going to use the sign thing, but if you'll notice here, this thing right here, x squared minus y squared over x squared plus y squared. If you think about those two, the numerator and the denominator there, here I'm subtracting y squared from x squared, and here I'm adding y squared to x squared. Does that tell you anything about what numbers this could be? Well, I know, because of the squaring and all that, that the numerator is going to be, well, I could, if x squared and y squared are equal, I could get 0 out of this, right? And everything's squared. I guess y squared could be bigger than x squared, so I think we've got a similar situation as we had with sine over here. Depending upon the x squared minus y squared, that's always going to be bigger than the top. You with me there? That's always going to be bigger than the top. If y is 0, yeah, I'm going to get 1. If x is 0, I'll get -1. Okay? But the x squared plus y squared is always bigger than the x squared minus y squared. We're talking about real numbers. So it's not ever going to be bigger than 1 or less than -1. You see what I'm saying? So that's I can see that. Okay. Well, that's almost what I've got there. Now though, I've got to have an xy. The thing about xy though is x times y could either be positive or negative, and that's going to if you multiply by a negative, it flips the signs, right? Remember on your inequalities. So let's multiply by xy, but we could separate it into two. There's different things I guess we could get, but so if I multiply by xy, and xy is say x times y is greater than or equal to 0. That's going to give me, so that, in that case, it's positive or 0, so it's not going to change the inequalities in here. So I'm multiplying by x, y, both sides. Right? That times xy, that times xy, and that times xy. And the inequality doesn't change because it's greater than 0. I didn't have to do that over here because it was x squared and that's always positive. Now, look at that. So the limit as xy approaches 0, 0. Take that limit now. what do we got? Same thing as we have over here, don't we? As xy goes to 0, 0, x is 0, y is that's 0. And of course, this is what we're trying to figure out. And that's even. So it's the same deal, you see. Same deal. It's both less than or equal to 0 or greater than or equal to 0. Now, that's for xy greater than or equal to 0, so let's don't. What about xy less than or equal to 0? Well, the only thing that changes is now, since I'm multiplying by a negative, let's see, greater than or equal to 0, the only thing that changes is the inequality. So I'm multiplying, here I multiply by the xy less than 0. So that just changes the inequalities, but does it change my result here? I don't think so. Because that limit as xy approaches 0 is still 0. This is still the limit as xy approaches 0, 0. It's still squeezed, isn't it? Because that's still 0. So both of these give me the same result. The limit is 0. So it's a interesting little method we haven't used yet, so I'll mention that. And there may be one on the homework then. Is that okay? Question or concern?